We have at long last reached rock bottom in our discussion of network layers. We are at layer 1, the physical layer. The physical layer is probably the one that we as computer scientists know the least about. It's the domain of the engineers and the physicists, so our coverage will remain superficial. In this video, as well as in the next, we will look at media, to get the feeling for how our messages are carried across from one computer to the next. And then after that, we still have to talk about signaling and a couple of other hardware-related topics. I am, as you know by now, a major proponent of the use of mind maps to visualize a topic. And one form of a mind map is a taxonomy. The taxonomy that I will develop here is one that helps us to think about media and the wide spectrum of media that is available. It's by no means definitive, and there are many other ways in which one can also develop a taxonomy. But in this taxonomy, the two major branches will be those media that conduct a signal, and then media through which a signal is radiated, so there's no conductor. On the conducted side, we can again think about two major categories. On the one hand, you have copper, and on the other hand, you have fiber, optical fiber. In terms of copper, many of the original networks, as you've already seen, for one reason or another, tended to use coaxial cable. More modern technologies tend to use some form of twisted pairs. And then we should not forget about the electrical signals, the electrical wires that are already installed in many buildings. Coaxial cable, as you will soon enough see, have been used in data communications in mainly two varieties. The thin, or let's start with the thick, and then in later years, the thin variety. Twisted pairs, the two most common variants that we are using there are the unshielded twisted pairs and the shielded twisted pairs. And we'll see what they look like in a moment or two. In terms of fiber, we can also look at various types of fiber, but we're not going to split that up right now. In terms of our radiated media, one can make a broad distinction between media that is directed, in other words, it is radiated from one point to another point, and then media that is used to broadcast information, in other words, to send it out in all directions. In terms of directed, we can ask what is being directed. Is it a form of light? Or is it some sort of electronic or electrical wave that is transmitted? In terms of light, we don't really see it anymore, but in days gone by, LEDs were sometimes used for data communication. But the more important one in the light category is arguably laser. In terms of electromagnetic waves, we have our microwave option. Also, and then to some extent, if we put satellite in here, then satellites tend to use microwave, so perhaps it would have been better to have classified satellite in terms of earthbound, or microwave in terms of earthbound and satellite. But this is not intended to be a definitive taxonomy, so this is good enough for our purposes. In terms of satellite, two major forms that we will speak about: low Earth orbiting satellites, so those that orbit the Earth and they sort of rise on the horizon, travel through the sky, and then set again on the other end. We'll speak more about how they work in a moment or two. And then there are the geostationary ones. Those are the ones that orbit around the Earth at the same speed at which the Earth rotates. So they are static in terms of the Earth. If it is above you now and the Earth turns for the next hour, that satellite will still be above you. Going to the broadcast category, obviously there we're thinking about things that are generally deemed to be radio wave-like, things like typical radio broadcast. And while it's possible to subdivide this extensively, one option here is to just say, okay, we've got Wi-Fi on one end, and we have cellular communication on the other end. And obviously with cellular we can go from 1G all the way to 5G. So this provides us with a picture of media, and our intention in this video is to look at conducted media, in other words, more or less everything to the left of this division. And then in the next video, we will look at radiated media, everything to the right of this divide. This picture shows what we've been talking about in a manner that is a little bit easier to decipher. Our first example of conducted media is copper cable. We've seen our example of coaxial cable that we used to illustrate buses on a couple of occasions already. Now, if you were to strip away this outer rubber plastic covering, you would see a lovely copper braiding on the inside. And that shields the inner conductor. And the inner conductor is there in the core. For example, when you get a lightning strike or something, the two are protected from another. If we were to strip away the copper braiding a little bit, then you will see that underneath the copper braiding is a layer of plastic covering the inner conductor. And then if we cut away this plastic on the outside, you can see the copper cable on the inside, the conductor on the inside, that is shielded by the braiding on the outside. This is the sort of cable that was used in the very early days to build computer networks. Very expensive. We used it to communicate at about 10 megabits per second, so it was a real waste. Over time, especially as cable TV developed in several countries, a thinner type of coaxial cable was used, and this thinner type looks exactly like this thicker type, except that it contains less copper. This was often referred to as cheaper net because it was significantly cheaper. In days gone by, we tended to refer to this thicker cable as, let's say, 10^5, because you could communicate at about 10 megabits per second over a distance, over a bus length of about 500 meters. This was 10^2, 10 megabits per second, and you could use it over a distance of about 200 meters. Over time, the speeds also went up to about 100. These are examples of old cable. In a more modern installation, you would probably use something like this. If you can read, this is unshielded twisted pair. And to buy this in hundreds of meters is not strange at all. So here is our example of what this cable looks like. And to open it up, and normally if you open it up, you will open up about 5 millimeters or so. I'm going to open up significantly more so that we can see what it looks like. And what you see on the inside are these pairs. So these pairs are obviously twisted around one another, so we can untwist them so that you get what you have there is green and white and green. There's orange and white and orange. There's blue and white and blue, and there's brown and white and brown. What is not obviously from this, or what is not obvious from this small piece that I stripped away, is that these pairs are also twisted around one another. The idea of that is the same as shielding, to reduce interference so that you could communicate without external sources exercising too much of an impact on this, or even internal crosstalk from occurring. Shielded twisted pair looks exactly the same, except that it has a shielding layer around it. Here I have a piece of coaxial cable that is often used to connect television sets nowadays to antennas or to dishes. You can again see the outside covering, and you can see how, or you can also see that there's a core wire in the middle. But most of this covering looks like aluminium foil. It's not nicely as robust as the previous example that we saw. But what we have here is more or less what you will see when you look at shielded twisted pairs. The twisted pairs will be in wire or in next to one another like that, and then it will be shielded by this something that looks very much like this foil. Unfortunately, due to the lockdown, I don't have an example of shielded twisted pair with me at this stage. Let's now look at how these media are connected to the computers. The thick net or the thicker coax cable obviously will form a bus, and you can literally connect to it anywhere. The thin net or cheaper net, as it's colloquially called, will also be used as a bus. The twisted pairs, whether it's shielded or unshielded, will be used with a hub. Welcome to my vampire clamp unboxing video. This may be a world first. So here is my brand new vampire clamp. It consists, or the packaging contains, an aluminium part, a plastic part, a black screw, And then the two most important things here, the teeth. So there we have a set of short teeth, and they're going to bite through the coaxial cable's outer layer into the copper braiding. And there's the long tooth. That's going to bite into the kernel, into that core, into that central wire in the coaxial cable. So let's unpack this and see what it looks like. There, as I said, is the plastic part. Let's install the short teeth. So they go in there, and there's the other short tooth, and it goes in there. And what we have now is something where the wire, the coaxial cable will be put into that slot, and you can see those little sticky points there that will bite into the cable. And okay, there's an easier way to do this. There's the aluminium part. You can see it has a part that can move up and down, so it will push the cable into that bottom plastic part. It's going to slot over the plastic part like that, and then as we apply the screw, which goes into that little hole, it's going to push that down, and as it pushes it down, it will force the cable into the short teeth. Here is our long tooth, and this is going to screw in on the bottom, and you can see that that tooth will go right through the cable and bite into the core of the cable. So let's do this. Get this out of the way, and you will remember that I've used this cable on a couple of occasions already as an example of a typical coaxial bus. And there's my plastic part, and I need some tools. So before we do this, let's just look at my tools. There's my drill. That's the sharp end. That's going to drill a hole through the outer part so that that long tooth can bite into the core without touching the braiding. Pretty sharp, so keep it protected. And this is also a spanner that you'll see I will use just now. Some instructions, and somewhere in all of this is our hex key that we will use to tighten the screw. So what I'm going to do now is I'm going to put my coaxial cable into that slot, teeth biting into it. I am going to slide this aluminium pressure plate onto it. Screw came out, so let's just put that back in, and just while I'm fixing the screw, chances that you'll ever encounter this in real life are very, very small, because this technology has been dead for so many, many years. So there I'm tightening the screw, and it is pushing the cable down into the plastic part, which has those short teeth pointing upwards. And as I tighten the screw, those short teeth are biting ever more tightly into my cable. Now we need to get the long tooth in. And for that, I will use my drill, and I'm going to put it into this plastic part, and I am going to drill a hole. So this goes through this plastic outer coating. It goes through the braiding, and it's just nice, long enough so that it touches the copper core. So nicely guided here. There's very little that can go wrong. And at this stage, I can put the long tooth in. So that's the part that's going to touch the core. It's going to go through that little hole that I've just drilled. And it fits into that slot. And this is where the other side of my drill, the spanner part, just to make sure you've seen it, what it looks like. And that's where I can now tighten it and struggling a bit to get a grip, but it's getting the grip, and there it's nice and tight, and it is biting into the core. This has been attached. What will happen to this now is the two teeth, or the two wires from the short teeth, are extending at the ends there. The wire coming from the long tooth is extending in the middle there, and this will now be put into a media access unit, and the media access unit will be linked to the computer, and it will convey the signal that is on the cable to the computer. In the meantime, while we don't have a media access unit ready and to put on, I can protect this. I guess these vampire clamps have been used for something else as well, because the 5 volts or whatever you'd get on the cable during network operation will definitely not give you an electrical shock. Ethernet was introduced after it was in use in the cable TV industry. And by that time, the cable industry or the TV industry already developed an easier way for consumers to connect to the medium. So the so-called BNC plugs were developed. B as in bayonet, and NC as in the names of the developers that very few people will recall without looking at Google, and this made it rather easy to use. So what you will do to make a connection is you will have a variety of connectors. There we, for example, have a T connector, and if I want to install my computer, what I need to do is between the two pieces of wire that previously would perhaps have been connected with a straight through connector, I can now install this T piece, and I can install my link out to my computer. One interesting thing, if you ever encounter this, because this has also become really, really scarce and it doesn't work, then chances are that you don't have the 50 ohm end connector in place. So at the end of every cable, it needs to be terminated with that 50 ohm. I think people years have been lost because many people didn't know about that requirement. Let's now talk about the medium that you are most likely to encounter in your day-to-day lives. UTP. Maybe you'll encounter STP more often, who knows, but UTP is indeed very popular. We're going to connect it first of all to an RJ45 plug, the standard plug that you use in typical networks. So in order to install it, we need to strip away a little bit of the cable. If you've got a professional stripper like this, it makes life a lot easier than trying to do it with a penknife. One word of warning is if you cut it with this, So you simply insert the wire, but if you cut it, make one turn. If you keep on spinning it, then chances are that you will cut one of the wires on the inside, and you don't want to do that, because if the wire is cut, then the connection will not work. You again see these twisted pairs that we've encountered previously, and we're going to untangle them, and they need to be inserted into this plug in the correct sequence. There are two standards that are in popular use. Both are the T568 standard, but then there's A or a B suffix. The A suffix is used in Europe, in South Africa, and so on. The B suffix is used in the United States, particularly popular with AT&T. For some reason, I got used to the B suffix standard, so that's what I will use. So once you've untangled these wires, there's a little trick if you want to do it as smoothly as possible, and that is to try and straighten out every piece of wire, all 8 of these wires, 4 pairs in it. Now, we've not said this previously, but on a 10 megabit per second connection, you will only use 2 pairs. On a gigabit per second, all 4 pairs will be in use. So straightening these out and then arranging them in the appropriate sequence depending on the standard that you're using. The first one that has to go up is orange in the B version of the standard, as I said, and then orange and white. That is followed by sorry, it should have been orange and white, then orange, then green and white, then blue, and there are the wires in the correct sequence. Now, if you were using ordinary RJ45 plugs, you would have to snip them so that they are flush, and then you could push them into the RJ45 connector. I'm using a new type of RJ45 connector that has little holes in the front, and as I push these wires into it, I don't have to push it until it is flush. I can actually push it through, and this makes it possible for me to verify that the wires are still in the correct sequence: orange, white, orange, green and white, blue, white and blue, green, brown and white, and brown. So once I've pushed that in, I should make sure that the sleeve is pushed well into this part at the rear, because I am going to crimp it. I'm going to do 2 things to it. The one, while crimping it, is to hold the cable, and the other one is to push these electronic, copper contacts into the wire to make a secure connection. As I said, these are rather special, so I need a crimping tool that will cut off the pieces that stand out in front. In a normal crimping tool, this just wouldn't work, and you can't crimp this with a normal tool, so the two has to go together. Pushing this into the opening, there's a nice flush fit. You can see the wires extending there, and as I crimp it, you can see the wires being cut off, so very tight grip, and the wires are indeed cut off, and my cable has been crimped. As you can see there, those metal contacts have now been pushed into the wires. if we just quickly look at the before picture, you can see those those connectors that look like little forks standing out, and in the after picture they are pushed into the cables, into the wires themselves to make a secure contact. However, you don't always want to crimp something into a plug. Sometimes you want to connect a wire to a socket, and a typical example may be something like this, where you have some sort of a mounting box and the sockets installed, and you have to make the connection. What you will see here is that this has two sockets, and on both ends you've got both of the wiring schemes and the color of the wire that needs to go into that little slot. So it's basically a matter of pushing the wire into every slot and then using a punch down tool to get it into position. Now, there are at least 3 different variants of these sockets, so for that reason you have to pick the appropriate punch down tool. They will look something like this, and one of the things to be very careful of when you use these punch down tools is that some of them have sharp edges. In fact, on most of them you can interchange them, so that you do get the sharp edge, and then as you are punching down, it can cut the wire on your behalf. This one's got a nice little scissor there that will cut the wire as you're punching down. So in principle, a very easy process, easier than fitting plugs, just putting the wires into their appropriate sockets, choosing the appropriate punch down tool, and then punching down. Makes a nice sound when you punch down, so that you know that it is clicked into position securely. These wall sockets, one example of where you want to punch down, but you also get modules that you can use on where we would normally install light switches and so on. Obviously, for that you need a different type of wall plate, so something like this. Maybe you've seen the wall plates on the wall behind me at some point, and in a lot of those cases they've got Ethernet sockets installed, so that I can just plug into a socket in any room, whenever I want to work there, when Wi-Fi is, for whatever reason, not strong enough. Once you've manufactured a cable, so you've installed your cable and either attached plugs or attach a socket or whatever, you want to test it. Now here I've got a cable that's been pre-manufactured, so hopefully this will work. And the way in which you can test it, well, there are a number of tests that you may want to conduct on this. One of the simplest tests is the question whether you have connected the wires correctly. So a typical tool, and this is a fairly low-cost example that I've got here, is one where you will have some endpoint and you will have the actual testing device, and I've switched it to check my wiring, and as I push the wires, what I should see is the 1 lighting up, the 2 lighting up, and so on. What I'm seeing here indicates a problem. So even though this is a commercial cable, something is wrong in it, and what that would typically mean with a homemade cable is that I've got to snip it off and attach a new plug on it. While I have this cable here, I can also demonstrate to you how I can use it for a different purpose. We've actually seen this tool before when I used it in the Ethernet demonstration, just to check whether, I used it to listen whether there was something on the medium. Now, if you've installed your cables throughout your house, then what you will find is that there are a lot of wires emerging into your wiring closet. And if, for example, you want to find the one that starts at the back of me, and you want to see where that one ends up in the wiring closet, then setting this to continue, I can test it on or turn it on, and I can turn my probe on. And what I can now do is push the scan button, and I can hear that there is a signal on it. So the usual thing would be now to go to my wiring closet, wiring cabinet, and I have 100 wires coming out there, and I can test this one and see that the signal is indeed on this one. In fact, the way in which you typically use it is you split the bunch of wires into two, and then you hold this into the one bundle and into the other bundle, and then you know in which bundle is your endpoint. And then in that bundle, you split that bundle in two again until you find the appropriate one, because it's pretty hard to trace all the cables from throughout your office complex or your house to all the various endpoints. Once you have installed your network, you'd really like to test the socket to see whether it is connected, whether everything works. It's also at a later point, once you wonder whether the socket is working properly, it helps if you've got the appropriate test equipment. This cable has been plugged into a wall socket behind me, RJ45 Ethernet port, and if I now plug it into the tester, you will see that it begins to test my network. You will see that it finds power over Ethernet, power port, the data link layer works, it's getting an IP address from the DHCP server, it's getting out via my router, and there it is talking to the cloud, to a machine out there. And since all of that is green, I know that this socket is working properly. Obviously, the latest and in all means the best technology for conducted transmission of data is optical fiber. Optical fiber is manufactured by taking a piece of glass, a glass rod that has been manufactured in a very special way, and then stretching it out until it is a couple of kilometers long, exercising strict quality control. There's a lot that we can say about the way that light stays inside it, whether it reflects off the sides, or whether it bends, or whether it is single mode where it doesn't even bend in the fiber. But those details are physics details, and we're not going to concern ourselves too much with that. As computer scientists, there's not too much that we can do about that. As an example of an optical fiber, here is a typical patch panel, and exactly how it works I will demonstrate in a moment or two. So this is real optical fiber, high speed. Here is something similar. This is so-called toslink. It is what you would normally use to connect a loudspeaker to a radio system if you don't want the electricity to interfere with your sound. Difference is that this is plastic on the inside, and therefore cannot be used for high-speed data communications, but is much, much easier to use for demonstration purposes. So let's look at this to illustrate how it works. Just before we do that, it's probably a good idea to talk about how optical fiber is installed. couple of ways, depends on the scenario. If you have optical fiber coming into your environment, it may come along the same poles that are used for telephone lines. It may be buried in cable or in underground. However, in many business setups, they're beginning to use these conduits that look like straws, and they install these underground, and then they put a fiber into it, and with high-speed wind pressure, they just blow it through this straw-like thing, and it emerges at the other end. And if you want to upgrade that fiber or whatever, you can install it without opening up your buried cable again. So let's now move to the quick demo of these two patch cables that I've shown you. So I've cut the lights. It will make the video much noisier, unfortunately. But what we can now demonstrate is, here I've got a normal laser pointer, and here is my Toslink cable, and I'm going to shine the laser into the Toslink cable, and with a bit of luck you can see the light emerging on the other end despite all these twists and curls. With the real optical fiber, because this is so much thinner, it is much harder to get everything aligned, but let us try anyway. So again, cable, I am shining the laser into the one end, and with a bit of luck, you can see the light emerging from the other side. Let me take you on a tour of the relevant parts of my house. As is so often the case, fixed line connections start at the telephone pole, and then they simply go through the air until they reach the house. There you can see an ordinary telephone cable and an optical fiber from the same pole. Both enter the roof cavity. Optical fiber goes out to the right. Let's just follow the telephone line, ordinary copper, the way we used to communicate for a long time. Best stage, that telephone line doesn't carry any data anymore. The optical fiber also goes through the roof cavity, following its own path. You can see that they've installed additional fiber there in case I want to move the end point of my fiber at some point. And there it enters my wiring closet. Clearly, I should have tied it up before showing you this video. There you can see some cables running through a conduit that's been opened up. Not a very full conduit, but still nice to have the ability to find a wire with a signal tracer. There's one specific wire going up there, and it reaches a wireless access point, one of a couple that are installed in the roof of my house. That wireless access point is powered by power over Ethernet. Typical use of power over Ethernet to power devices that are situated in places where you cannot easily access them, specifically where you cannot easily power them, where there's no easily accessible power outlet. The same is true for security cameras. They're typically installed in places where you don't have power, and you also want to power those through PoE. But we'll talk about wireless access points in the next video. This was our rather quick and somewhat superficial introduction to conducted media. In the next video, we will look at radiated media.
Music